We talked about scheduling in a batch environment. Today we're going to talk about scheduling in an interactive environment, or in other words, when users or some other entity needs to interact with the processes. So we have interactive scheduling. The first approach is called Roundrobin. And you can see in the figure here, we have B, which is the current process. When B has finished up its time slice, or what we call the quantum, then B gets moved over to the end of the queue and has to wait for all the other processes to run before it can run again. So some terminology, we have quantum. And that's the amount of time each process is given. Now, what if the quantum is too short? Then we have too much context switching. So too much time wasted in context switching, which is simply changing from one process to the other. So if we have 1 millisecond for a switch and 4 milliseconds for a quantum, then we're wasting 1/5 of our time. What if the quantum is too long? Then it means that the job is going to have to wait a long time. So for example, a new job waits a long time. Has to wait for all the other jobs to finish. Not just new jobs, but any job has to wait a long time once it's at the beginning of the queue. But we do have good efficiency. In other words, we're not going to waste much time context switching. So our goal is a balance. So goal is to balance between efficiency and responsiveness. And a good, most systems have quanta in the range of 20 to 50 milliseconds. That's round robin. Another approach to scheduling is called priority scheduling. Where we run the highest priority jobs round robin style. So let's look at what that looks like. So we have process A, we have process B, we have process C, and we have process D, D, and those are all of high priority. Then we have a couple here that are of mid priority, and then a few that are low priority. And what we're going to do is we're going to run all of those, and then as soon as we're done with all the high priority jobs, we'll run the mid priority and then the low priority. Now, there's an obvious problem. Doesn't this cause starvation? Starve processes, specifically processes of low priority. In other words, are those jobs ever going to get a chance to run? And the answer is yes, it does. Of course, but we can take measures to minimize that problem. In fact, we can get rid of the problem entirely. And the way we do it is we can lower a job's priority each time it gets a quantum. Or equivalently, we can raise a priority the longer a job waits. To get a quantum. And so the priorities are actually going to be changing as we go. Now, something to keep in mind is an I/O-bound process. Consider an I/O-bound process. And as a reminder, an I/O-bound process is one where you have small spurts of CPU, right? So this is CPU right here, and then this right here is I/O. And we're going to get a little bit of I/O, a little bit of CPU, and then some I/O, and so on. And so what's going to happen is these processes may not use up their entire quanta each time they get it. And so we want to make these high priority so that they run often, but not for very long. And we can do that by setting the priority equal to 1 over f, where f is the fraction of the time used in the last quantum. So, for example, suppose a process in its last quantum, f is equal to 2 over 50, or in other words, 50 milliseconds. It was allotted in the quantum, it used only 2 of them. Therefore, the priority would be 1 over f, which is 1 over 2 over 50, which is 50 over 2, which is 25, a high priority of 25. The next approach is called multiple queues, which I think is a little bit strange. It's a little bit of a strange name. So let's take job A. And suppose it used up the entire quantum. Then we want to run it less frequently. But with larger quanta, or with more quanta. For example, so suppose job A needs 100 milliseconds to complete the job. So the first time it runs, it's going to be given one quantum. Then it'll wait some time, and since it used up the entire quantum, we think, okay, well, let's give it 2 this time. And it uses it all up, so we wait a little bit longer, and the next time we give it 4. Wait a little bit longer, next time we give it 8, wait a little bit longer, next time we give it 16, and so on until it completes the job. Now, job A is going to finish about roughly the same time as it would have had we just run it with 1 quantum. But it's more efficient to do it this way overall. So for the whole system, we have gains in efficiency. And similarly, what if job B is I/O bound? Then we want to run more frequently. More frequently with 1 quantum. Okay. So the result is we're going to end up with something that looks like this. So over here on the left, we have I/O bound processes. And on the right, we have CPU-bound processes. And of course, there's a lot of gray area in the middle, right? This is a spectrum. As we increase the CPU boundedness, I don't know if that's a word, then we're going to increase the number of quanta. And as we become more and more CPU bounded, we're going to decrease the priority. So I/O-bound processes have high priority. They're going to get run more often, but they don't get as many quanta, whereas CPU-bound processes have more quanta, but they're lower priority. They don't get run as often. Now, we could ask ourselves, well, how do I know if a process is I/O-bound or CPU-bound? And it's exactly as we showed up above here, whether the job used up its entire quantum, or how many of the last X quanta used up entirely, and so on. The next approach is shortest job next. In the book, it calls it shortest process next. And it's simply that. We're going to run the shortest job first, or run it next. Now, the problem is, how do we estimate how long a job will take? We could ask the job, how long are you going to take? And of course, the developers of the job, of the process, the writers of the code, are going to say, oh, I hardly take any time, because they want to get to run first. So we can't rely on that. So we have to rely on running multiple times. So, for example, let's let T of I be the time taken on the ith run of process A, of some process. So let's make a table. We have job time and we have estimate. So if we run a process, the first time we run it, we don't have an estimate. We don't know how long it's going to take. And let's suppose it takes time t0, that run. Well, the next time we come to run the job, we have an estimate. We can say, oh, our estimate is that it will take about time t0. Now, once it finishes the second run, then we can get an even better estimate. We can say, oh, let's average those two runs, and that will be our new estimate for how long the job will take, and that's T2. Once T2 finishes, what we could do is we could average the 3 runs, but we want to weight it. We want to use what's called aging. Because when T2 ran, the state of the system was different, and it's probably fairly similar to what the state of the system is now. The state of the system was different back when T0 ran. And so what we want to do is weight T2 more heavily. So we're going to do this: T0 divided by 4, T1 divided by 4, and T2 divided by 2. So it's a weighted average. Now when we run T4, we'll do a similar thing. T0 divided by 8, T1 divided by 8, T2 divided by 4, and T3 divided by 2. So T3 is weighted more heavily. And so the time it took on that run will have more of an effect on our estimate than all the other runs. Another approach is guaranteed scheduling, which is actually hard to implement in practice, but it's a good principle. If we have n processes, let's guarantee that you get 1 over n fraction of the time. Now this is hard to implement, difficult to implement, because n is changing all the time. Implement. N's changing. We're adding processes. Processes are finishing. We have to keep track of how long a process is taken. Then we have to keep track of, it's a moving target. So n is a moving target. So an answer to that problem is lottery scheduling. And it's easier to implement. And the idea is to give each process some number of lottery tickets according to its priority. Then it's a lottery system, right? If you have more tickets, there's a greater chance you'll get selected to run the next time. The nice thing about lottery scheduling, not only is it easier to implement, but it's very responsive. So a new process has a very good chance of running. And that is interactive scheduling.